pleasure today to have Mike Grudić with us. Mike's PhD here in Caltech at Memorial University. He spent some time at CITA before. He was a summer student here working in Pairwise for years here. He's currently at Caltech doing and today he's going to tell us about simulating the formation of massive star clusters. Thank you.
Thank you very much. I'm very happy to be here at CITA, and thank you for coming. It's a completely different group of faces than I knew 5 years ago, but I'm very happy to see that the same friendly CITA culture persists. This is work that I've done with my advisor, Phil Hopkins, as well as various collaborators, including just the FIRE collaboration at large. So if you know about the FIRE project and the simulations and you're interested in chatting about those later, I'm happy to do so, even though I'll be talking about some different stuff today. Right, so these are the objects I want to talk to you about today. So young massive star clusters are star clusters that, well, they're young. They're less than 100 million years old. So they more or less should bear the imprints of their formation events. And thus, we should be able to learn something about star formation by studying these things. They tend to have a wide range in masses. We found them as large as 10 to the 8 solar mass. In our galaxy, it's more around 10 to the 4. But across the different mass scales, they actually look remarkably similar to each other, which is quite interesting and tells us something a little bit about the physics that form them. And these things account for a fair portion of the recent star formation in galaxies. So if we want to understand star formation at large, a really good place to start is just to look at young massive clusters. So there are a lot of big questions about star formation. This is a very incomplete list. I would say one of the trickiest ones that we can learn a little bit about by studying young massive clusters is the stellar initial mass function. So why do we get different numbers of stars of different masses? Now, I'm not going to talk about that today. It's a very tough problem and too tough for me. But David Guseinoff and Mark Krumholtz have some very interesting things to say about that. Another question is, where do globular clusters come from? In particular, it seems very natural that the young star clusters we observe today might resemble how globular clusters that are billions of years old originally looked at high redshift. But to answer that question, we first need to understand the physics of the initial formation of the clusters before we ask ourselves, how do these things evolve over billions of years? So the sorts of questions I'm going to talk about today have to do with these very basic questions about the nature of cluster formation. So I want to talk about star formation efficiency. So how many stars do you form per unit mass that you put in gas? Is cluster formation slow? Is it fast? There are sort of two schools of thought on that. And just what determines the masses, sizes, shapes, bound fractions of star clusters that form in different environments? And ultimately, we have all these different physics that are going to be relevant. We have gravity, we have hydrodynamics, we have cooling and chemistry, magnetic fields, stellar feedback. So if we want any hope of disentangling the roles of these physics, then we really kind of need to do simulations and construct a laboratory. So yeah, in this talk, I'm going to be just answering some of these very basic questions about bulk properties of star cluster formation. So essentially, my problem is this. We have some self-gravitating ball of gas that is prone to gravitational collapse. And we know that some stuff happens, and eventually you end up with more or less relaxed state star cluster that forms. And all this stuff in between is tricky to simulate because of all the physics involved, and also sort of tricky to observe because, one, it's obscure, and two, it is a relatively fast event in terms of galactic timescales, so it's hard to catch it in the act. So what I've been doing is simulating star formation at high resolution with the GIZMO code using the framework for stellar feedback, cooling, and star formation developed for the Feedback in Realistic Environments project. So the code we're using is GIZMO, which is a multi-method, multi-physics, spatially adaptive MHD gravity code. And these show you just sort of the gamut of different types of problems that have been run with GIZMO. It's very much modular multi-physics code ported from Gadget. And what's special about GIZMO is that it provides a framework for solving conservation laws in a meshless way so that your resolution elements move with the fluid. So the idea is that you have a sort of scheme for assigning different parts of the simulation domain to each particle. So this green area belongs to this particle, this blue area belongs to this particle. And from that partitioning scheme called a partition of unity, you can construct the effective faces between two particles, which you can then determine the flux and evolve any sort of conservation equation. So when I talk about conservation equations, I'm talking about anything in this form where we have some sort of stuff which has some sort of flux and possibly a sink. And we can essentially take this equation and with this discretization turn it into this form where we can evolve the quantity. So this is the framework underlying basically all of the physics in GIZMO other than the gravity. So we're using this to solve the fluid equations, momentum, mass, and energy. We're using it to solve the MHD induction equation. The simulations I'm talking about today don't solve the diffusion equation, but that's been used for other fire simulations. Essentially, anything where you can come up with a flux conservative scheme, you can theoretically put into this meshless framework. But let's talk about why we actually want to do this in a meshless way. Yes?
So is this defining of the boundaries between the regions? Of course, it's meshless, but is it somewhat like the Voronoi moving mesh?
Yes, actually. So the Voronoi moving mesh is a special case of this. Essentially, the moving mesh is where these boundaries aren't blurred at all, more or less. So you just have these well-defined geometric faces between the collocation points. Whereas this is more like superficially a cross between that and SPH in that we're finding however many nearest neighbors, and we're doing all these calculations within that kernel. So the hydrodynamics we use in these simulations are a Lagrangian MHD scheme. And there's a lot of reasons why we really do want a Lagrangian scheme for this sort of problem. We're following the collapse of a molecular cloud to form very dense substructures. And we expect that these substructures are ultimately going to map onto the ultimate structure of the star cluster. So what we really want is for the resolution elements to follow where the mass is going. And that's exactly what you get in a Lagrangian scheme. Whereas if you have a scheme where you're solving at collocation points that are fixed in space, then you can end up with a situation where all of the mass goes into one cell and you're not really resolving anything. Another nice thing about this Lagrangian scheme is that we're going to be dealing with really high Mach numbers. So the canonical Mach number of a GMC in the Milky Way is something like 30. Now, these Lagrangian schemes are Galilean invariant, which means you don't have these error terms that grow at greater Mach numbers. Whereas these grid codes tend to have slower convergence at high Mach numbers. So you need to run a bigger simulation to get the same accuracy. But really, the thing that's going to probably change the dominance from AMR codes to Lagrangian codes in the coming years is the fact that if you have a Lagrangian scheme, then if you're solving a fragmentation problem where you need to resolve the Jeans mass, then the scaling is much more favorable. With a Lagrangian scheme, if you want to resolve a gene's mass that's 10 times smaller, you give it 10 times more resolution elements. With a fixed grid scheme, or an AMR scheme, you need 1,000 times more. So most of the significant calculations in star formation theory in the past few years have been on AMR codes, but as we press to higher and higher dynamic ranges, that's probably going to change a bit. But of course, the reason that these are so favored is that they're easier to implement, easier to make stable numerically, and straightforward to add extra physics. So the way that we're going to handle star formation in these simulations is actually not by resolving the formation of individual stars. So what we do is we have the cloud discretized into these gas particles, and we evolve the motion of these gas particles according to our conservative equations. And every time step, we check what is effectively the local gene's length. So the local gene's length is the smallest length scale of fragmentation. So essentially, we're checking whether we can resolve fragmentation. If we can, then the gas particle carries on. But suppose it contracts to higher density and the gene's length can no longer be resolved, then the gas particle is suddenly eligible to turn into a star. And it will do so stochastically with a constant probability per unit time of 1 per free fall time. So we'll end up with this star particle, which might represent 10 or 100 or 1,000 solar masses. So we're not doing individual stars, but rather we have these collisionless particles that we assign IMF average properties for purposes of feedback. So radiation pressure and radiative heating turn out to be very important sources of feedback in this problem. The way we do it is via a scheme called locally extincted background radiation in optically thin networks, or LeBron, because Phil Hopkins is from Cleveland and he's a big Cavs fan. Essentially, it's a combined local and global approach where we solve the problem within the kernel of a star particle's nearest gas neighbors, and we essentially handle all of the really high opacity UV photons within this kernel, whereas the stuff that doesn't necessarily experience a very high opacity field ends up escaping the local environment of the star particle, and that stuff gets to see every other particle in the simulation, and it's essentially propagated throughout the simulation domain in the same way as we solve for the gravitational force. Is there a question?
Oh, I was wondering how you were treating the opacities in this. Were you treating it as a gray opacity? Were you treating it as a band of gray opacities? Or were you treating it in some other manner? Were you treating it with like a whole spectrum of opacities?
So we essentially have different bins of gray opacities. So we handle the UV, the optical, and the IR separately. So each of those experiences its own opacity. Roughly, each one is roughly 10 times less opaque than the last. And yeah, we handle all of them independently. So like, because the opacity for UV is so high, most of it gets absorbed here, whereas for the IR, not so much, and it ends up going farther into the simulation domain.
It makes more sense to divide the spectrum into, so you can ask for each frequency what the optical depth is, and if it's less than the size of the cell, it would make more sense to take all that part of the spectrum and just inject its energy, increase the pressure of that cell.
Yeah, so that's effectively what we end up doing without doing that checking. But you're absolutely right that you could easily make this scheme more aggressively adaptive in that sense. Something worth thinking about for sure. So the effects of the radiation are as follows. The UV photons are going to create H2 regions heated to 10 to the 4 Kelvin, which are going to create bubbles that drive out the gas. And that's a particularly important effect mainly for GMCs with escape velocities not much greater than 10 kilometers per second. So certainly for some Milky Way GMCs, that's probably an important effect. The other effect is radiation pressure. So both the UV and the IR photons mainly will drive outflows just directly with the pressure from photon absorption. And we have a bunch of other radiation hydro methods in development that essentially do these things in a completely different way. So the hope is that we can run with all these different methods and actually compare how they behave on this problem. So stay tuned for that. But there's more feedback. So essentially, we handle all the other ways in which stars can inject mass, energy, and momentum into the ISM. The star particle, again, just sees its nearest neighbors, and we just inject those quantities via the sort of flux conservative scheme. So that includes supernova explosions, which will dominate energetically the feedback budget at later times, generally timescales greater than 10 million years. Now, supernovae are particularly important for preventing the runaway collapse on galactic scales. In general, we haven't found that they're quite as important as other feedback mechanisms in this problem because the timescales are relatively short. The other thing we have is stellar winds. So we account for both the line-driven stellar winds from OB stars, which are fast and quite powerful, and also the slow AGB winds, which last longer and are more gradual, but are important for enriching the ISM at later times. So what we've done is a suite of simulations where we start with a gas ball with an initial seed velocity field, and we let it collapse and form stars. So the orange stuff you're seeing here is gas. The little blue knots are star clusters. So what happens is that the cloud collapses. It forms stars. Eventually, it forms so many stars that essentially it overshoots the Eddington limit, and the cloud self-destructs. And we've run these simulations over a wide parameter space of surface densities and spatial scales to sort of understand what aspects of this problem depend on what quantities.
So this is just a completely isolated cloud, no galaxy.
Correct. So the first question I want to talk about is star formation efficiency. So what fraction of the initial gas mass that you put in actually ends up getting converted to stars? So we have decently good estimates of this for molecular clouds in the Milky Way. It appears to be somewhere around a few percent or around 1% per freefall time. Now, this figure of 1% makes it very tempting to draw an analogy with the result that we get for galaxies. So it's been found that galaxies typically form stars such that they use up 2% of their available gas mass per freefall time. So we can quantify that with this quantity epsilon FF, the per freefall star formation efficiency, which is the ratio between the star formation rate you actually get and the star formation rate assuming all of the available gas collapses. So we get this same sort of figure for galaxies, but on the other hand, the nature of feedback moderated star formation in galaxies is somewhat different. So here's a plot from a simulation where they varied the strength of stellar feedback in a full galaxy simulation. And what we're plotting is the star formation rate with 3 different feedback strengths. And what is found is that regardless of the strength of feedback, the star formation rate is more or less constant in the galaxy. But if we triple the strength of feedback, the star formation rate is 1/3. We double the strength of feedback, the star formation rate is 3 times greater. So it reaches this sort of quiescent mode where it's in a steady state where the turbulent dissipation balances the momentum and energy injection from supernova explosions mainly. But if we look at another one of these movies, we can see that at no time does this event really reach anything resembling a steady state. And the reason for that is that there's nothing really stopping the cloud from forming so many stars that it overshoots the Eddington limit and eventually destroys itself. So the quantity we're particularly interested in this problem is what I call the integrated star formation efficiency, which is the ratio between the final stellar mass we form and the initial gas mass that we had. So we expect that if cooling is efficient, then we'll have predominantly momentum-conserving feedback. And what you can effectively do is come up with an effective force of feedback, which is just proportional to the mass in live stars that you currently have. And you have this one parameter determined by the IMF in stellar physics that parameterizes the strength of stellar feedback. Then what we do is we just equate it with the weight of the gas, and we figure that around the time when this force of feedback is equal to the force of gravity, the cloud will destroy itself and cease to form stars. And when you solve this, you find that the star formation efficiency should be predominantly a function of sigma, the surface density. So essentially, it should scale with m over r squared for these clouds that we've set up. Now, the question is whether this should actually work, because this is making quite an assumption, because there are so many different types of stellar feedback, and like nothing is exactly momentum or energy conserving. So it's very much an approximation. However, if we plot this star formation efficiency versus everything we can think of, essentially, we find that the surface density is indeed the tightest predictor of the star formation efficiency. So each one of these points is a simulation. We've run them at different surface densities. And we find that the star formation efficiency is small at low surface density, and it saturates to about 1 at high surface density. And we've also plotted this as a function of escape velocity, density, mass, and radius. And none of these really predict the star formation efficiency with the same accuracy.
This calculation does not take into account the porosity of the cloud.
Porosity?
Yeah. So if you go density spectrum, because you can see that you have very complicated structure on many scales, and so of course, this
right.
In stars, you know, the porous atmosphere allows you to exceed the active limits. So in the same sense, you can make more resilient to feedback.
That is correct. So, like, you're right that, like, we're only looking at, like, this average density, and, like, you can derive a different density if you consider, like, the mass-weighted average density, for example, and that should certainly interact with the radiation field in a different way. However, this, like, we're forming all sorts of substructure in these simulations, so we do expect that some of the effect of the substructure of the ISM should be captured by these simulations. And like,
so is the predominant source of force in the simulation the direct radiation pressure, which is most consistent with the
it appears to be, yes, and that's actually where we were getting. So essentially, we had those results for the star formation efficiency, and we want to isolate which physics are actually responsible for that. So on the left, I'm plotting the star formation history, so the star formation rate as a function of time, in runs where I've varied the strength of stellar feedback overall. So I actually find something quite similar to what we find in galaxies, where if we double the strength of feedback, we halve the star formation rate, and vice versa. And if there's no feedback, then essentially the cloud consumes all of its gas within a couple of free fall times. On the right, what I've done is different simulations where we make different modifications to the physics that we put into the simulation. I won't go into great detail about all of these, but the point most relevant to what you mentioned is that if we include only radiation pressure as a source of feedback, then we get a very similar star formation efficiency to the reference run. So it does appear that, at least in this problem, that appears to be the most important feedback mechanism. However, I should also add that this was a cloud with an escape velocity much greater than 10 kilometers per second. So conceivably, in cloud with a smaller m over r, photoionization heating would also be very important. And we've mentioned these two different star formation efficiencies, the per free fall and the integrated. And what we essentially find is that they're two sides of the same coin. They're directly proportional to each other. So the reason for this is that the cloud can always find a way to form enough stars to blow itself up within a certain number of free fall times. So whatever that number of free fall times is, that's whatever this factor relating the two is going to be. And we get a similar figure of 3 free fall times when we look at actual GMCs in the Milky Way. So to summarize this star formation efficiency stuff, we find that the star formation efficiency is predominantly a function of the surface density of the cloud, and that relation is due to the relative scaling of the strength of stellar feedback and gravity. And because of the essentially the dynamics of the cloud destruction, we get this proportional relation between the two different types of star formation efficiency. So you might have noticed that you had these dense blue knots forming in the simulations, which are hopefully something actually resembling star clusters. So that's the next thing that we took a look at. Do these clusters that form look like actual young massive clusters? So canonically, the way that they fit these young massive clusters is with an Elson profile, which is just a constant density core with a power law tail fall off. And the slope of this power law one can call shallow if it's close to 2, essentially, because the value of 2 would correspond to infinite integrated mass. And what is found is that the slope of this power law fall off in actual star cluster populations typically lies in the range between 2 and 4, with a median of about 2.5. So it is an observational fact that the mass profiles of young massive clusters are quite shallow. So it's an interesting question to figure out how they get this sort of density profile.
But if yours have an outer edge, then they can't be anywhere close to -2 forever, right?
That's correct. Like eventually, there has to be some sort of truncation. But it's another question entirely whether you can actually constrain that truncation from your fit, which is, I have the impression, is pretty tough to do. So we've looked at all of the star clusters that form in the simulations, and we find that they actually fit quite well to this same Elson 1987 surface brightness model. And what's more is that we can look at the cumulative distribution of the slope of that density profile. So I mentioned that most of them are between 2 and 4, with a median around 2.5. So these dashed curves are the simulations, which form entire populations of star clusters, so we can get these statistics. And the solid curves are different observed populations of young massive clusters in M83 and the Magellanic Clouds. And what we find is that the simulations with stellar feedback get more or less the same distribution of profile slopes. So we can say that at least down to the form of the mass profile, we're getting fairly realistic looking star clusters in a coarse-grained sense. So we want to understand why they actually have this sort of structure. So to do that, we can look back at the simulations and observe how these clusters actually form. So you see that you have this very clumpy substructure forming, and eventually the substructure merges together to form one monolithic, relaxed star cluster. So the process of star cluster assembly appears to be a process of, my favorite oxymoron, violent relaxation. There are rapid changes in the gravitational potential, which allow the system to exchange energy between its different components. And you have this merging together of substructure to eventually form the final star cluster. So we have this picture of hierarchical star formation, where we have gravitational collapse, which produces these dense subclouds, which eventually form subclusters, which start to blow out the gas around them due to stellar feedback. And eventually these subclusters merge together into one big cluster, and all of the gas gets blown out. Now, to understand why we actually get these very shallow mass profiles, we have to essentially understand this in the context of collisionless self-gravitating systems, which means, strictly speaking, it obeys the collisionless Boltzmann equation. And the reason why I invoke collisionless physics is that these simulations aren't resolving individual stars. So we really are sampling the collisionless Boltzmann equation in a Monte Carlo sense. So the collisionless Boltzmann equation says that the phase space density in the vicinity of a star is conserved along its trajectory. However, what happens is that these elements in phase space can get stretched out by the dynamics of the system and essentially deformed to such a degree that if you look at this on any realistic scale, it looks like this has been diluted compared to its original state. So what actually happens if you look at the coarse-grained phase space density is that it can only decrease in the evolution of the system. So you can essentially put together an analytic argument based on this and show that when two star clusters merge together, you have to end up with a star cluster that had a shallower slope than you started with. So here we're plotting the final slope as a function of the initial slopes of two star clusters that merge. And the point is that whatever assumptions we make, these two curves lie below the line of equality, so we always have to end up with a shallower slope. So then we wanted to sort of validate this argument with simulations, so what we did was a set of collisionless star cluster merger simulations where we started with two star clusters with a Plummer profile, which has a slope of 4. And we merged them together, and we got a star cluster with a slope of 2.69. We merged those together, and we got 2.48. Merged those, we got 2.21, and so on. So we do get this process of profile shallowing as these elements of substructure merge together into one final cluster. And if we look at the distribution of mass in phase space density, we see that this shallowing is associated with a sort of flattening of the distribution. In other words, we're spreading mass across many different orders of magnitude in phase space density. And that was great, but then we decided, okay, can we actually construct a sort of toy model of star cluster assembly that ends up giving us the same result? So what you're looking at is a simulation where we came up with an idealized fragmentation model to set the initial substructure of the mass distribution, which you see here, where it's tightly clustered. And then we just let it relax under gravity, and the subclusters merge together into a population of larger clusters. And we've done this in such a way that we capture the essential spatial and kinematic scaling relations observed in nascent star clusters. And what we find is that the star clusters that assemble in this process do have the same sort of profile with a slope close to 2. So essentially, it seems quite plausible that this hierarchical picture of star cluster assembly is sufficient, although possibly not necessary, to reproduce the mass profiles of star clusters.
You made a very general argument just now about these tails always becoming shallower, but I mean, in classical picture of gravitational collisionless interactions, you can have these runaway collapse of the denser parts of gravitating systems, and it's accomplished by throwing out some stars basically off to infinity.
Yes.
Right? So if you then didn't necessarily track those things, the ones thrown far out in phase space, but focused on the collapsing core thing, I would assume that you could get steepening profiles in some cases. So in your sort of argument you just made, where does it kind of break down, or why does it apply to this case but maybe not to all cases, or should it apply to all cases?
Well, essentially, the hope is that the time scale we're interested in is shorter than the relevant time scale for the effects you're describing, which is, at least naively speaking, true in that young massive clusters haven't experienced any significant number of dynamical relaxation times. So essentially the picture is that the collisionless dynamics sort of give you this background morphology that you're starting out with, but then obviously you will end up having this interesting stuff going on over longer time scales.
This doesn't appear to apply to galaxies.
Well, galaxies are just collisionless in any sense, regardless of time scale.
No, I'm talking about your profile. You don't get collisionless.
So actually you get something quite similar in that we have a surface density profile with slope -2.
And the outermost parts of the head.
Yeah. So actually, it's quite plausible that you can invoke a similar argument to justify the -3 slope of the NFW profile. However, obviously, the inner profile is completely different in a galaxy than it is in a star cluster, unless you have a core, like in a core dwarf. So to summarize what we've found about star cluster structure and star cluster assembly, we can reproduce. Oh yes, was there a question?
Just wondering, how does the dynamical timescale of the individual subclusters compare to the Riemann timescale? I'm wondering if they're able to relax at all the central main points.
Right. So at some scale, like for example, if you have a triple system or a binary, like you can't describe that system as a collisionless ensemble. So certainly this has to break down at some scale. As far as these simulations go, we never really reach that point just because we're sampling phase space with so many of these collisionless particles that we don't pick up those effects. But yes, certainly at some scale, the dynamics don't look like this collisionless Boltzmann picture. So this collisionless Boltzmann picture is sufficient to get us the proper mass profile, but there could be other stuff going on. And yeah, what we also found is that star clusters have a variety of different slopes in their mass profiles, and these just seem to have emerged stochastically from star formation physics, because we run one simulation that produces a population of clusters, and we get this wide range of different slopes. And since we're essentially only invoking gravitational physics, we should end up with the same result whether we're talking about a 10 to the 4 solar mass or 10 to the 8 solar mass cluster, which is good because there doesn't seem to be much relationship between the shape of a cluster and its mass. So the last thing I want to talk about is a collection of relatively preliminary results, but I think are pretty exciting. I want to talk about the problem of forming a bound star cluster. So this would be an example of a star cluster that is probably bound. It's more or less spherically symmetric, although there's a bit of substructure that probably won't last too long. So this cluster is presumably going to more or less stick together for a decent amount of time. Whereas this guy is just in the process of flying apart, and you don't expect any discernible substructure to survive for very long as it disperses into the galactic field. So the question is, what decides whether you get one of these guys or one of these guys? So the quantity we're interested in is gamma, the cluster formation efficiency, the ratio between the total stars formed to the stars that end up bound in clusters. Now, probably the most well-known piece of theory on this problem is due to Dietrich Croysen, and he argued that more dense, extreme star-forming environments should form a greater fraction of bound star clusters. So down here, we're not very dense or having much star formation. Up here, we have a lot of star formation, and essentially 70% of all of the mass in stars is going into bound star clusters. Now, this has come into question, in particular in the past year, because it's been shown that when we're looking at these guys, we're actually looking at relatively young clusters. So the idea is maybe these guys just haven't had enough time to get destroyed, unlike this population, which is older. So this is a subject of relatively active debate, but we can say something about the physics with the simulations. So what ultimately determines the cluster formation efficiency will be the star formation efficiency, because if you blow out all the gas, you lose your gravitational binding energy, the thing flies apart. The gas evacuation time, if it's slow, then it's easier to remain bound. If it's fast, it's harder. The dynamical state of the star cluster, so is it virialized, is it cold, is it hot, and the clumpiness in substructure from which the star cluster assembles. So recall that in the second act of this talk, we had this plot where we have this dependence of the star formation efficiency upon surface density. So we should expect that there should be some dependence of the cluster formation efficiency on surface density. But on the other hand, the surface density of molecular clouds within a disk galaxy doesn't actually vary that much in the region where you see most of the star formation. So a possible explanation for why we're not actually seeing very strong evidence for a scaling in the cluster formation efficiency is the fact that we just don't see much diversity in the surface density of these GMCs. Now, if we look at the actual results from the simulations, on the left we have the star formation efficiency we talked about earlier. On the right we have the cluster formation efficiency. So we do find that when we plot this as a function of surface density, at low surface density we have low cluster formation efficiency. So down here, essentially, only 1% of your mass is going to form a bound cluster. When we go up to more Euler-like surface densities, where star formation is very efficient, we put, again, this same figure of 70% of our stars into bound clusters. So what's interesting is that this figure of 70% emerged by a completely different mechanism than was proposed in the Croyson 2012 paper, because essentially we get this right at the star cluster virialization. We have these stars that have been ejected as the star cluster assembles itself, and this 70% just seems to be this magic number of the fraction of mass that survives that violent process. And we ran this at both solar and 1% solar metallicity, which mainly affects the effect of stellar wind feedback. So at low metallicity, the stellar winds from OB stars essentially have no dynamical effect. And it seems to make it easier to form bound star clusters. Whereas at high metallicity, we have more winds from OB stars. In fact, the effect is comparable to radiation pressure. And that seems to really make it hard to form a bound cluster. Now, we do have to be careful about sorting out the different physics mechanisms that ultimately affect this. But the main point to take home here is that it's basically the local strength of stellar feedback that is going to determine this cluster formation efficiency. And whether we get 10% or 1% will depend on the details of how that stellar feedback works. And the last thing I wanted to say about cluster formation is that it happens in a highly efficient regime. So this is the per free fall star formation efficiency as a function of time to star cluster formation for an ensemble of star clusters from my simulations. So you see that the star formation efficiency starts out low, but then it gradually ramps up until it's something like 50%. So in other words, the process of star cluster formation is a process of essentially runaway star formation where feedback can no longer really prevent gas mass from ending up in stars. And then it's just over because you've used up all the gas locally. So
what's the comparison going on here? So when if you're at the same time blowing some material away, is that being counted in that's no longer counted, right? Because it's no longer in the...
right. So what we're counting here for the gas mass available at any given time is the gas mass within the half-mass radius of the particles that end up forming the star cluster. Now, that could conceivably bias things toward the stuff that's in the more inner region where it's denser. But that's sort of a problem that's hard to get around because ultimately any measure of star formation efficiency is an accounting problem. So yeah, it's tricky. Do you count the gas that's in the very diffuse medium surrounding the cloud, for example? Because that will bring down your estimate. So yeah, it's important to be clear what you're actually talking about when you are talking about star formation efficiency for that reason. But yeah, presumably if I had a more conservative accounting, then it would probably be more in like the tens of %. But the point is that it's certainly nothing like galaxies where it's of order 1%. So to summarize the formation of bound star clusters, we expect that gamma is going to depend on all these different things, but because we have these simulations, they don't have to be free parameters anymore because we're following the process of star cluster formation from start to finish. We get this maximum cluster formation efficiency of 70% just due to the process of the hierarchical assembly of the star cluster and the fact that stars just inevitably get ejected in this process. And the actual dependence of gamma on the environment is going to depend greatly on the specifics of the feedback physics. But essentially, the idea we can run with in this picture is that denser environments should probably produce denser GMCs with higher surface density, which should then go on to have high star formation efficiencies and have large bound fractions. Now, what's nice about this problem is that there's a lot of recent data that's come out of both the molecular clouds and the young massive clusters present in disk galaxies. So essentially, we can compare the two populations and try and figure out what the mapping from one to the other is. So stay tuned for this paper. So to summarize, we've settled on this picture of massive star cluster formation where we have fragmentation, collapse, we form stars and subclusters. These subclusters assemble into one big star cluster, and feedback ultimately blows out some fraction of the initial gas mass. So we can do this problem without resolving individual stars and still get things that look very much like actual young massive clusters. The process is very clumpy, violent, and not at all spherically symmetric. It's fast. It only takes a few freefall times. It's highly efficient despite stellar feedback because of this scaling of star formation efficiency in dense regions. And it's an inherently multi-physics problem in that you really need to get the hydrodynamics, the gravity, and the feedback all right if you want the whole picture. So in summary, simulations are providing a self-consistent picture of star cluster formation from start to finish. And I'd be happy to take your questions. Thanks.
Thank you, that's really nice. And we'll be taking Mike out to dinner later if anyone wants to join us to talk some more.
Sorry if you said this and I missed it. Did you also simulate the formation of open star clusters to get, because you talked about the bound star clusters, but do you have ones that are predominantly open, and is that just the low star formation ones?
Yeah, so like essentially you're always going to get some mixture of open and bound star clusters. The open ones are just the ones that for whatever reason don't make it, so the gas blows out and the stars fly apart. So if we're forming like 10% of stars in bound clusters, part of those stars that didn't end up in bound clusters were ejected from those bound clusters, but also another great part of them were just never in a bound cluster to begin with.
So what was the range of, like, what were the physically densest clusters you got?
So essentially, we're still at the knob tuning phase where if we have a denser simulation and it's going to produce proportionally denser star clusters. However, if we start with something that looks like a Milky Way GMC, so 1 million solar masses, maybe 100 parsecs across, we get things, we form these star clusters that have like 10 to the 4 solar masses within a half-mass radius of a parsec. So they do seem to be within the range of realistic YMC densities.
So that's getting to the globular range, right?
Yeah, it's similar to some globulars. And if you simulate a more extreme event, of course, you will produce a denser star cluster. Yeah.
So in the initial conditions, you have this sort of uniform sphere which with a velocity field.
Mm-hmm.
Without the velocity field, that thing would just collapse wholesale into a single place, right?
Yes.
But with the velocity field, you produce differences between locations within it. So my question is, how much of the evolution of the star clusters do you think depends upon the initial conditions you prepared for the study, like to different drive turbulence for a while and then let it collapse?
Mm-hmm. In my experience, basically none of it. So we've tried essentially all the things one can think of when investigating this. So different power spectra. You can start with self-consistent turbulent box initial conditions. And what tends to happen is you form essentially a hierarchy of bound substructures where the source of the turbulence is not what you initially gave it, but rather the gravitational collapse. So essentially, we always end up attracting to this same sort of behavior regardless of the initial seeding that we give it.
As long as you give it some seed.
Yes, exactly. Because obviously, like the physical solution for no seed is just going to be monolithic collapse. So presumably, if you gave it too small a seed, then perhaps you would imprint those initial conditions. But as long as, yeah, it would be very artificial because GMCs are not lambda CDM where you have a small seed.